Welcome to this video. Here we are going to discuss about toy problem in AI. A toy problem is intended to illustrate or exercise various problem solving methods. It can be given a concise or exact description about the problems. It's a puzzle like a problems, simple and useful for analysis. It illustrates various problem solving methods and used to compare performance of the algorithms. Example, 8 puzzle problem, sliding block puzzles, towers of an eye, n queens problem, chess, missionaries and cannibals problem. Here, we'll discuss about 4 problems, an interesting one. The first one is about camel and banana problem. Here, problem description is given. We'll read. A person has 3000 bananas and a camel. The person wants to transport the maximum number of bananas to the destination, which is 1000 kilometers away, using only the camel as a mode of transportation. The camel cannot carry more than 1000 bananas at a time and eats a banana every kilometer it travels. What is the maximum number of bananas that can be transferred to the destination using only camel? No other mode of transportation is allowed. This is a problem description. In pictorial representation here, we have 3000 bananas, then one camel. The market is 1000 kilometers away from the farmer's place. Then camel can carry a maximum of 1000 bananas at a time. It eats one banana for every 1 kilometer. Now, what is the maximum number of bananas that can be delivered to the market? Here we have 3000 bananas. It can carry only 1000 bananas, then 1000 kilometers. If we load 1000 bananas here, then it will travel 1000 kilometers. Then end will get 0 bananas. Remaining we have 2000 bananas. This is a problem statement. So what are the assumptions we can have? Okay, we have total of 3000 bananas. The destination is 1000 kilometers, only one mode of transport. Camel can carry a maximum of 1000 bananas at a time. Camel eats a banana every 1 kilometers. Then he cannot allow the camel to carry 1000. Then the end we have nothing. So we can have some suggestions. So with all these above points, we can say that the person won't be able to transfer any banana to the destination as a camel is going to eat all the banana on its way to the destination. So we can have a trick. Instead of traveling at the stretch 1000 kilometers, we can have some intermediate point. Okay, there we can load 1000 bananas to the camel. We can have some intermediate point, then come back, get next 1000 and store it, and again come back. So after loading some bananas here, you can have intermediate point or you can reach the destination. So it is not possible to carry 1000 bananas to reach the 1000 kilometers. Nothing will be there. Camel cannot come back to carry remaining 2000 bananas. So have some intermediate points to solve this problem. So here assume we have two intermediate points or three or one. Okay, anyway we have to find what about the number of bananas will be reach that market. So 3000 bananas, assume we can take some intermediate point P and Q here. Then the assume the 3000 bananas we have to keep in that intermediate point P. We don't know what about the distance of P from A. So with some assumption of X value, we'll proceed. This may be some Y value. This may be some Z value. So we'll calculate what is X, Y, Z. Anyway, X plus Y plus Z is equal to 1000. That we know. So here assume we have 3000 bananas. The camel can carry 1000 bananas here. Then coming back again second 1000 and coming back and third 1000. Anyway, some bananas will reach the P point. Assume in terms of 1000, either 2000 or 1000. If we take a the P distances away from Jena, it can reach 1000 manas or some short distance we can have the 2000. Assume here it traveling three times from this side, two times this side. So totally it has to travel 5x times and assume we have the 2000 manas here. Okay, either it can have 2000 or 1000. Here I am assuming that after traveling 5 times of x distance, the camel is having 2000 manas at P point. Then what about x value that we have to calculate? So totally we have 5x. Yx means first 1000 manas it carrying, then it eats 8x manas. Again coming back to get this second 1000 manas, again it eats x manas, then coming and again coming back, and so there are 5x times it's traveling and it eats 5x bananas also. So here 3000 minus 5x is equal to 2000. So 5x is equal to 1000. We can get this x value is equal to 200. Simple formula. Totally 3000 bananas. It traveled 5x times and it's keeping 2000 bananas at P point. So 3000 minus 5x is equal to 2000 because it traveled 5x times. So it ate 5x bananas. With this calculation, we will proceed from P to Q. Okay. So again, it's having 2000 manas. So it first time it's carrying 1000 manas here. Then coming back, eating some manas, y number of manas. Again, taking second 1000. So it travels 3 times of y distance. So and also it ate 3y bananas. So we can have this formula like 2000 minus 3y is equal to 1000. We have to calculate y is equal to 1000. It's around 333. Okay, so 2000 minus 3y is equal to 1000. Then y is equal to triple three. It cannot eat 0.331 us. So we'll round this value. We'll take 333. Now here the value of this A to Q is 200 plus 333. It's around 533. Then 1000 minus this value will give you the Z value. Okay. So 1000 minus 533, the Z value is 467 since the total distance is 1000. Then it travels, so remaining you have 1000 and bananas. Then it travels 467 kilometers, so it ate 467 bananas. So when you take round of 1000, so 1000 minus 467, so we have 533 bananas. So the farmer can sell 533 bananas in the market. Okay, this is a way we can solve this problem. Second problem is about missionaries and cannibals problem. The problem description is three missionaries and three cannibals find themselves on one side of a river. They have would like to get to the other side, but the missionaries are not sure what else the cannibals agree to. So the missionaries manage the trip across the river in such a way that the number of missionaries on either side of the river is never less than the number of cannibals who are on the same side. The only boat available holds only two at a time. How can everyone get across the river without the missionaries risking being eaten by the cannibals? This is a problem description. So we have three missionaries and three man eaters. All six they have to cross the river using one boat. We have some assumptions. The number of cannibals should lesser than the missionaries on either side, maybe equal. Only one boat is available to travel. Only one or maximum of two people can go in the boat at a time, not more than that. all the six have to cross the river from bank. There is no restriction on the number of trips that can be made to reach the goal. Both the missionaries and cannibals can row the boat. So, with this assumption, how do you find the solution? So, this is a scenario. There are three missionaries and three cannibals. One boat, it's a river, bank one, and they have to travel. So, they have to reach this river bank to this side. So, it's the initial state, the river, left hand side, all the six people are standing, and the goal state, the river right hand side, all six has to come. Take this one. This is the way we are going to solve. Initially, we have three missionaries and three cannibals in the river bank 1. The river bank 2, no one is there. Then we can select one missionary and one cannibal from this side. Okay, they can row the boat. They are coming this side. Now boat is here. They have to send the boat to this side. So select one missionary and send here. Now here we have three missionaries in riverbank 1 and two missionaries cannibals in this bank 1 and only one in this riverbank 2. Now the boat is here. We can select two cannibals and they are sending this side. Now here the riverbank 1 three missionaries and riverbank 2 three cannibals. Then they have to send the boat to the next side. So they are selecting one cannibal. It's rowing the boat coming this side. Now we can select two missionaries. They are coming this side. Okay, so every time we have to check whether the number of missionaries are equal or more than that cannibals. Otherwise, the cannibals will eat the missionaries. Then here we have to select two cannibals. They are coming this side. Again, they are sending two missionaries this side. Now we have C and one C and triple M. Again, send the C here. Okay, triple C is here. Then the two C's they are coming this side. Then one C is taking a boat coming this side, and it's taking two C this side. Finally, we have all six and that is three missionaries and three cannibals reach that riverbank too. This way we can solve this problem. We'll go to the next problem, water jug problem. It's an interesting one. You are given two jugs, a 4-gallon and 3-gallon, a pump which has unlimited water, which you can use to fill the jug and ground on which water may be poured. Neither jug has any measuring marking on it. How can you get exactly 2 gallons of water in 4 gallons of jug? Okay, this is a problem statement. How do we solve? Here we have 4 gallons of jug and 3 gallons of jug. The description is about no measuring mark. Then we have a pump to fill more water. We have to get exactly 2 gallons of water in 4-gallon jug. Okay, here we are having some numbers x and y. Maybe x is a 4-gallon jug and y is a 3-gallon jug. The starting state, both x and y are 0 and 0, and goal state we have to get exactly 2 gallons of water in this 4-gallon jug. Okay, the operations we can perform: emptying a jug, filling the jug, or pouring water from one jug into another jug. We have more number of solutions in this problem. We'll see one problem solution. Assume x and y, as I said, x is a 4 gallons of water jug and y is a 3-gallon water jug. Initially, these two are empty. That is represented x is equal to 0 and y is equal to 0. Then we can fill this 4 gallons jug with 4 gallons of water. Then now x is equal to 4, y is equal to 0. What you can do is you can pour this water to this jug. Now we have 1 gallons of water in this 4 gallons of jug. The remaining 3 will be poured into this 3-gallon jug. See, we have 1 plus 3, 4 gallons of water. But 1 gallon in this 4 jug and 3 gallons in 3 gallon jug. Then we can pour this water out. So this will become 0. The 3 gallons of water will be 0. Now we can pour this water into this. Now we have this empty 4 gallon jug and 1 gallons of water in that white jug. Again, fill this 4 gallons of water in that 4 gallon jug. Pour some water into this. Now we have 2 gallons of water. The remaining 2 will be poured into that 3 gallon jug. Then pour this water out. We have only 2 gallons of water in this 4 gallon jug. This way we can solve the problem. Okay. Here finally we got that solution. X is equal to 2, y is equal to 0. We have other possible solutions like 0, 0, 4, 0, 1, 3, 1, 0, 0, 1, 4, 1. Finally we have 2 gallons of water in this 4 gallon jug. Again we have one more solution for your reference. Then the next toy problem is 4 queens problem. We have also 8 queens problem, n queens problem. We'll take simple one 4 queens problem. Here the problem description is about we have 4 by 4 chessboard and number of rows of chess 1 to 4. We have to place 4 queens in this grid and such a way that should not attack each other. That means it should not be placed in the same row or same column or diagonally that should not be placed. So we have to place 4 queens such as Q1, Q2, Q3 and Q4 on the chessboard such that no 2 queens attack each other. In such a conditional, each queen must be placed on a different row, that is, we put queen I on row I. For example, assume I'll start to place this queen here, then second queen may be here, and third queen I cannot place here because it's going to attack this one. If I'm to place this third one here, it's going to attack. If I'm to place it here, it's going to attack. So this plan will not work. Backtrack again, try another solution. If I'm to place this Q here, then second one may be placed here, and third one may be here, and fourth one. Now these queens are not placed in the same row and same column, so it's not going to attack. So we have more solution in this. This way we can arrange this 4 queens problem. This can be extended with 8 queens also. So with this, I'll complete toy problem. Thank you.